Hello and welcome back to moment generating functions. In this video we're going to talk about joint MGFs or joint moment generating functions. And so now we have two variables. If x and y are random variables, the joint moment generating function for x and y is defined in a very similar way to the moment generating function for a single random variable. So we have m sub xy of, now we need two dummy variables, s and t. And so we have the definition here as the expected value of e to the sx plus ty, right? And so that is very similar to when we have a single variable, the moment generating function of a single variable x is the expected value of e to the t times x. So now we have a sum in the exponent, e to the sx plus ty. And sometimes you'll see that written sort of t1 and t2. It doesn't matter what you call those variables. They are sort of dummy variables anyway, and the s and t just are a little bit of a lighter notation than the subscript notation. So this expected value is calculated exactly the same way that the single variable one is calculated, and that is by lotus, except obviously now you're using a multivariable lotus. So you put the exponent e to the sx plus ty in front of the density function if x and y are continuous, or you put it in front of the PMF, the mass function, if x and y are discrete. And similar to the one variable case as well, the MGF formula must be finite. Somewhere this has to be an open disk now instead of an open interval around the origin. So let's go and investigate a little bit further. So the first part here, we're not going to prove this just like we didn't prove it the last time, but if the joint moment generating function, if it exists, it completely determines the joint distribution of x and y, right? In other words, for any pair of random variables x and y, the moment generating function is unique for their two distributions. And this generalizes as well. So to n variables, you can have the joint moment generating function of x1 to xn, and now I will use the subscript notation. It's the expected value of e to the t1x1 plus t2x2 all the way up to tnxn. So there's nothing more that you need to do, except of course you'll have a n-dimensional density or PMF function, and you'll have n integrals or n sigmas when you need to calculate these things. So let's look at a little discrete example. Suppose that x and y have joint PMF given by this table here, so p of xy, and we're going to calculate the joint moment generating function for x and y. So the definition, right? This is the definition of the joint moment generating function, the expected value of e to the sx plus ty. So because this is discrete, we are summing over all x and y pairs, over all x and y values of e to the sx plus ty times the probability mass function. And so if we go and take here, this is the when x is 1 and y is 1. So the probability p of 1, 1 is this, and the coefficients are 1 and 1. Right? This is when x is 1 and y is 2, and so on. This is p of 1, 2 is there, and the 1 and 2 are the coefficients because the x and the y values become the coefficients, right? There they are, the coefficients. So you continue all the way through, and you will get this as your expression for the joint moment generating function of x and y. Now, that doesn't tell you much about what good it gives. That'll be a little bit later, but let's do one more definition, this time in the continuous case. So we're going to apply the definition of the joint moment generating function to x and y, which have joint density, this. So now I give you a little bit of a warning. I don't say calculate the joint moment generating function. I say apply the definition, and we're going to see why when we get to the end of the example. So here is the density. It's 2 on this support, which turns out to be that triangle right there, and 0 otherwise. So using the definition of the joint moment generating function is the following. So the expected value of e to the sx plus ty integrated over the support. This is lotus that we're doing here. So the integral from minus infinity and minus infinity to infinity becomes over the support of the variables. And so from x is equal to 0 to 1 and y is 0 to x of here is the exponent, e to the sx plus ty, and this is the density, right? The density there is just 2. So we go ahead and calculate this, first of all, by splitting using a law of exponents. We can split this as a product of the two exponents, and then we go through and crunch through the definite integral, which we have done so often now. I will spare you the details, but we're going to come up with this as a final answer. Now, we've applied the definition, and as far as I can tell with my calculations, we've done it correctly, but this is not a valid moment generating function. Why? Because it doesn't exist at 0, 0. You cannot plug in s is equal to 0 and t is equal to 0. You cannot. And so that's not to say that there might not be some way of fixing it. We're not going to look any further at that here. We'll use this just as an exercise to calculate the joint MGF, and we'll leave the fact that this is not valid, we'll leave that alone. So what we're really interested in doing though is using these joint moment generating functions, and to be able to use them in any sort of effective way, we need to know something about their properties. So there's 3 properties here that we're going to take a look at. And the first is the marginal MGFs, the marginal moment generating functions. And so the marginals, just like the marginal distributions, they end up by corresponding with the single variable, right? So when I write m sub x, that is the moment generating function, the MGF for x, which you would get if you considered x alone. And the same thing here, this marginal moment generating function with y for y is the MGF of y if you would consider y alone. But considered in the context of joint distribution, they become the marginal MGFs. And so the way that you can calculate those without necessarily calculating the marginal density functions or marginal mass functions, if we're talking about discrete, is by using this property here of the joint MGF. And that is here that if you plug in 0 for the opposing variable, right? So if I plug in 0 for t, and t was the coefficient attached to y, then I get the MGF, the marginal MGF for x. Same thing here, if I plug in s is equal to 0, that s was the coefficient attached to x, and that ends up by giving me the density, the marginal moment generating function for y. And so the proof of that is quite straightforward. Let's do it in the first case where we plug in t is equal to 0, which means that we've got e, the expected value of s x plus ty, but t is 0. So of course that term just goes away, which is the expected value of s times x. Using lotus, that is the function e to the sx times the density function, and this is a constant as far as y is concerned, so we can bring that out of the integral, which leaves the inner integral with respect to y of the density function. That was exactly the definition of the marginal distribution for x, and the definition here of a function times the density, not just any function, but this function e to the sx. That's the expected value of s. Oopsie, no, it's not. The expected value of e to the s x considered only with respect to x, and that is the definition of the single variable moment generating function. So by analogous reasoning, by absolutely analogous reasoning, if you plug in s is equal to 0, you will get the marginal moment generating function for y. So first property, the marginal's second property, is related to something that we saw as well with joint distributions, and that is if these guys, if the x and y are independent, well, something nice happened. We had this property, right? If x and y were independent, then the expected value of any function of x times any function of y, if x and y were independent, those expected values could be multiplied, right? That was the property that we had for independence, and that, since moment generating functions are based on expected values, it might not come as any surprise that that property transmits itself to moment generating functions. And so the property is this, that the joint moment generating function is the product of the marginal moment generating functions, if and only if x and y are independent. And that also makes us think it is not the same property, but it is exactly analogous in form. We had the joint density f of xy is the product of the marginal densities if and only if. In fact, that was the definition. If and only if x and y were independent. So that is nice that the form is kept the same, but the reason is based on the property of the expectation. So we're going to prove it. We're going to prove it in one direction only. It's an if and only if. I'll prove one direction, and that is this one. If x and y are independent, then the joint moment generating function of x and y is the product of the marginal moment generating functions. So here, the proof is actually nice and short and sweet. We don't have to go into integrals or double sums at all. We can use the properties of expectation. And so the expected value of e to the sx plus ty, using your law of exponents, you can split that up into a product. And if x and y are independent, that's exactly the property I was talking about. I had reminded you up here. Then we have two functions, right? A function of x and a function of y. And if e, the expected value, if x and y are independent, then the expected value can be split up. The expected value of a product is the product of the expected values, and so you're using that property here, and each of those is the definition of the marginal expected, the marginal moment generating functions. Oof, there's a lot of vocabulary. I have to concentrate to say it correctly. So number two is a property of independent variables. Secondly, or thirdly here, sums. If w is x plus y, if w is a sum of two random variables. So w itself is a new random variable, right? This is a new random variable which is created out of two other random variables by summing them together. So in fact, w is a function. W is a function of random variables, but is a very specific function. It is a sum. So for general functions, this property is not true, right? This general functions h of xy, if we have a very specific type of function, if we have a sum of two random variables, then the moment generating function of w, which is, right, if w is x plus y, sometimes this is written as the moment generating function of x plus y. Notice this is a single variable, right? W is a single random variable. It is created from two others, but it is a single random variable, and so there is a one-dimensional moment generating function. And that is here, this is a joint. This is the joint MGF of x plus y, and so there are two variables that have been plugged in as the same, right? In other words, s has been plugged in so that it equals t, right? So this is, we have one variable in each of these cases, and we have one variable here because the second variable has been made equal to the first. So the moment generating function, the moment generating function of a sum is the joint moment generating functions with the two parameters, the two variables set equal to each other. And so the proof of that, again, just using expectation here, is if we have this, right, the definition of the joint moment generating function of two random variables has two variables s and t, and that was the expected value of e to the s x plus t y. And if we set s equal to t, then we get tx plus ty, which lets us factor out the t, which obviously we cannot do here. If s is not equal to t in general, there is no factoring to be done. But here we can factor out the t, and then we have x plus y, and x plus y, right, is how w was calculated. And so we have the expected value of t times w, of e to the t times w, the expected value of e to the t times w. There's two e's there, right? And that I have to concentrate so much. The expected value of the exponential, expected value of e to the tw, well, that's the definition. That's the definition of the moment generating function for w. So three properties. Let's review those three properties. First property, plugging in zero, and you get the marginal moment generating functions. Second property, if x and y are independent, then the product of the marginal MGFs gives you the joint MGF, and vice versa. I think. I'm not sure about how my grammar just scanned there, but you understand the properties written there. And lastly, if you have a new random variable that is a function, a specific function of two others, it is a sum, then you can get the you can get the single variable moment generating function for your new variable w from the joints by plugging in t for both parameters. Now, putting 2 and 3 together, and expanding to n variables, expanding to n variables, we get this result, which is going to be very important in the next lesson when we start trying to figure out distributions for some of these variables that are created by summing. And so we have this: if x and y are independent random variables, if x1, x2, and xn are independent random variables, and if w is their sum, so is the sum of x1 to xn, then the moment generating function of w, right, well, we said you could plug in t for all of the variables, that's property 3, but then property 2 said if they're independent, you can multiply the marginals together. So putting those two together, and we get this result. So we're going to keep that in mind for later use, and we're going to finish off with an example here, which is a bit of a word problem. So let's go through. A company insures homes in cities, J, K, and L. I live in Jburg. Yeah, no. So strange names for these cities, but there you go, J, K, and L. Since sufficient distance separates the cities, it is reasonable that losses occurring in each of these cities are mutually independent. Also, somewhat magically, the moment generating functions for the loss distributions in each city are known, and they are known to be these. So the moment generating function for the losses in J is given here as 1 minus 2t to the minus 3. The moment generating function for the losses in city K is given as you see here, and in city L as you see here. What we are asked to do is find the expected combined total loss from the three cities together. So we're going to go and apply some of our properties. So we're going to say that J, K, and L are not only the city names, but they are random variables that represent the losses in each city. X, if we want X to be the total loss, if we want to be the total amount of loss, then X is the sum. X is the sum of the loss in city J plus city K plus city L. Using the fact that these are independent and that X is a sum, the property that we had right above here tells us that we can know the moment generating function for X, and that is the product of the moment generating functions for J, K, and L, all with the same parameter t. And so using the formulas above, which are conveniently given to have all the same base, we can just add the powers together. And so we know the moment generating function for X. And now we're back in the single variable case. Once we know the moment generating function for X, we can use it to calculate moments. In particular, the first moment is the MGF of X, the derivative of the MGF, M prime, evaluated at 0. So we calculate M prime here, we get this, and then we evaluate it, we plug in equals 0 at t equals 0, and we get 20. 20 what? I don't know, the units weren't told to us, but they are some sort of monetary units. 20, 100, 20,000, $20 million per, who knows, 20 monetary units. One last thing that I want to point out is that X here, X just as W in the properties, is a new random variable, and it's created in this example from random variables J, K, and L. So it is a function. It is a function of them. X is a function of J, K, and L. It's a very simple function. It is their sum, but it is a function nonetheless. Now, just like when we use Lotus, when we have functions of random variables, finding the distribution and therefore calculating probabilities for X is potentially very difficult. Calculating moments and expected values, well, that's pretty easy. We can do it with Lotus, and since MGFs are based on Lotus, we can do it with MGFs as well, which is all that we were asked to do up here. We were not asked to calculate the distribution of X. We did that a little while ago in the univariate case with some transformations, but calculating the distribution of X and therefore probabilities might be quite difficult. And so, in general, moment-generating functions and joint moment-generating functions let us calculate moments pretty easily, but they do not give us information about the distribution of X in general, except that sometimes they do. Sometimes they do. In a few very specific circumstances, they do. And we're going to look at some of these circumstances in the next lesson.